Okay, so let's look at this problem. Again, we're going to draw the shear force and bending moment diagram for this. To get started, what do we have to do? We need to find our reactions. So I'm just going to shortcut this a little bit and go ahead and draw in my positive shear at A and my positive shear at B. I don't need to do anything else. So I'll just use this diagram as my free body diagram for my reactions. And I'll come over here and I'll go ahead and sum the moments at, we'll do it at A. So looking at summing moments about A, using right-hand rule for my sign convention, this 600-pound force creates positive or negative moment? Negative. So I got a 600-pound force. And what is the moment arm from A? 10 feet. Then I have this moment applied. What kind of moment is that with my sign convention? Negative. So I'll have minus 4,000 pound feet. And then I'll have my positive shear at B, which creates negative moment. It has a moment arm of 20. So what is the shear at, I wrote A, but it should be B. So what's that? That's 200 and 300, 500? Negative 500. So the shear at B is negative 500 pounds. So I can come next and sum forces in the Y direction. Make sure that's in equilibrium. So I have the shear force at A acting up, the shear force at B acting down, and I have minus 600 pounds. So that says the shear at A is 100 pounds. That makes sense? Okay. So let's draw our template for the beginning and end of our structure. What other points might be of interest to us? Well, probably this concentrated load. As we go from the left side to the right side, there's going to be a change. So let's include that. And that will help our shear diagram. What about this applied couple? What's going to happen to our moment diagram there? Probably going to have a big jump too. So let's add that one in. So now I can come back and I'll establish a positive x-axis and a positive shear axis, and we'll make all of our units in pounds. So starting on the left-hand side, what is the shear at A? 100 pounds. And don't forget our guiding principles here. We know that the change in shear is the area under the load curve. What's the area under the load curve for the first 10 feet? Zero, so no change. So at 10 feet, the shear should be 100. We also know that the slope of the shear diagram should be equal to the load. And that load is?
100.
Nope. 0. So that means we would have 0 slope. So over the first 10 feet, we have constant shear equal to 100. Now, as we go from the left side of the 600-pound force to the right side, what's the change in shear? Yeah, and that kind of force is negative, so it's going to drop down to negative 500. Now, the change in shear from 10 to 20 feet is the area in the load curve. And what's the value for the loading? 0. So there should be no change. This should stay minus 500. And the slope, right, is given by the load. And what's the load? 0. So it's got 0 slope. So there's my shear diagram. So what's the moment diagram going to look like?
Yeah.
So I'll go ahead and draw my positive x-axis. Positive moment. Our moment will be in pound feet. What's the moment at A? 0. And the moment at B? 0. Now our principle for this diagram is that the change in moment is equal to the area of the shear diagram. So, over the first 10 feet, what's the area of the shear diagram? 1,000, right? 10 feet times 100 should bring us to, let me draw this in a way. Let's see. Okay, we'll say here, 1,000. And what is the slope? Well, we know the slope in the moment diagram is equal to the shear. What's the shear? Constant and positive. Okay? Now the change in moment from 10 feet to 15 feet, I'm stopping here because there's an applied moment there that's going to cause an effect in our diagram. So over this first 5 feet, what's the change? What's there in the shear diagram? 5 times 500, that's negative 2,500, right? So 1,000 minus negative 2,500 brings me to negative 1,500. And the slope of that diagram is the shear, and the shear is constant and negative. Now, as I go from the left side to the right side here, I have this clockwise value for 4,000, which should make a positive jump. So, negative 1,500 plus 4,000 brings me to 25. Now the change in moment from 15 to 20 is the area under this part of the diagram, which is negative 25. Yay! And what's the slope? It's equal to the shear, and the shear actually has the same slope as this previous line. So these two slopes are the same. And if you looked at it, it would be minus 500. This one would also be. But here's your moment.
Why is it 4,000? How did 4,000 positive?
So wasn't our orientation the other way?
Yeah.
Say that again.
Like we established the
Clockwise moments create positive jumps.
Always the positive was counterclockwise.
That's sign convention for bending moment, but an applied clockwise moment creates a positive change in the moment.
Always?
Mm-hmm.
Yes.
What would happen if we did negative? We would be here at 1,500. We would subtract 4,000. We'd be down at 55,000, right? And then we would subtract another 2,500. We'd be down to negative 7,000 moment at B. Can we have a negative moment at B?
No.
No. We already knew it had to be 0. But by definition, a clockwise applied moment creates a positive jump in our moment diagram. It's one of those things you've got to know. Plus, works out. You couldn't have done it the other way. It wouldn't have worked out. That's another thing. You got two things going for you. Any other questions about this one? What? Oh, you have a question? I'm sorry. Or are you guys just having a discussion? Oh, okay. All right.